All right, do you have an answer? Why equations 3 and 4 exist? Right, I heard somebody is. Kirchhoff's, as I remember, it was like this: Kirchhoff's current law, or Kirchhoff's current law, KCL. Right? Those two equations are all because of this. Okay, if you look at this circuit here, let's change to another color. If you draw a closed circle in this way, then you can understand that these are the three currents flowing through this circle. IK is always equal to, and that's the flowing into the circle. Okay. And IG and IK, I'm sorry, this is IK. IK is flowing out of the circle. IG and IA are the currents flowing into the circle. So that's always existing. And then the second one, if I draw another circle here, okay, another circle, and IA is the current flowing into the circle, and must be equal to the other two currents flowing out of the circle, right? There are only these two currents, IC1 and IC2. Those are the two currents flowing out of that circle. So equations 3 and 4 exist. And combining all these four equations, you can get equation 5. IA can be written as this equation. If we do not consider, if we neglect these two parts, because those currents are usually very small, then the current flowing through this arraysure can be represented by IG and alpha, the transfer coefficient or transport coefficient of those two transistors. So in this case, when there is no IG, then alpha is very small. Alpha is also 0. Then nothing happens. Or in the beginning, when you inject a small current of IG, in the beginning, both alpha 1 and alpha 2 are very small in the beginning. They are very small. And therefore, IA will also be very small. The current will be very small. But when you inject a reasonably large IG, then you have both alpha 1 and alpha 2 getting larger. When they get close, alpha 1 plus alpha 2 is getting close to 1. Then this lower part, this is called denominator, the denominator part will be approaching 0. When alpha 1 plus alpha 2 is approaching 1, the total denominator will be approaching 0. And therefore, IA, the transistor current will be very large, and the arraysure is turned on. Okay, that's the physics of operation if we get into the details of some equations. This equation is usually used to illustrate, explain the operation principle. Okay? There are other methods to turn on the thyristor. Okay. Other than, so far, if you remember, the conditions for us to turn on a thyristor is to have thyristor between A and K subjecting to a positive voltage. You have to apply positive voltage between A and K. That's the first condition. Second condition, you are injecting current into the gate. In that way, you can turn the thyristor on. But actually, there are other methods to turn the thyristor on other than injecting gate current. These are the methods that we usually want to avoid. We do not want a thyristor to be turned on in this way, because these are the things we cannot control. We want to turn the thyristor through the gate terminal, through injecting gate current. So these are the things we want to avoid. For example, if you apply too high voltage across A and K, that will introduce avalanche breakdown. If that voltage is too high and exceed the limit this thyristor can sustain, then that will break down the thyristor. Breakdown means this thyristor is just like a short circuit or just like a switch turned on. Second, if the voltage across A and K is increasing too fast, that will also turn on thyristor. What do you mean by increasing too fast? Increasing too fast means du dt is too high. This derivative of the anode voltage over time is too high. That means this voltage is increasing too fast. Then that will also cause the turn on of thyristor. Even if you do not inject gate current, you just apply a positive voltage to A and negative voltage to K, and that voltage is increasing very fast, that will also turn it on. That's not good. We do not want that to happen. Okay. Third one, high junction temperature. When the junction temperature in the semiconductor is too high, then this will also be turned on. That's not good either. Okay. The last one, light activation. Oh, this is the only exception. Light activation. This thing is good, actually. That means if we do not inject gate current, but if we only introduce a light beam, introducing a light beam, and shed that light on the gate area in the semiconductor, in the silicon, in the thyristor semiconductor area, you shed some light, certain light on the gate area, that will be equivalent to injecting current. So, introduce some light beam on the gate area is equivalent to injecting gate current. This is good. Why is this good? Can you imagine that? In what sense this is good? I still have the control. I still can control this thyristor, but I'm going to control this thyristor not through injecting current, but through injecting light. And when you have light to control electric circuit, that will be very good to handle high voltage situation. Very high voltage. This is very good for very high voltage situation. Do you still remember when we talk about the structure of a power electronic system? I mentioned that the current and voltage you are applying to the power semiconductors are usually very high. But the current and voltage the control circuit can sustain is usually very low. Therefore, between the control circuit and power circuit, we usually need isolation, electric isolation. Otherwise, the high voltage and large current flowing through the main circuit might destroy the control circuit components. So usually we need isolation between control circuit and main circuit. And one of the isolation method is what? Is to use optical. Optical means using light. Okay. Therefore, if you use light activation to turn on a thyristor, that means you are using the control circuit and the power circuit is isolated. The control circuit is just generating some light, and that light will be used to turn the thyristor on or off. Okay. So light activation can be used to make. This is used to make a very special thyristor, which is called light triggered thyristor. Light triggered LTT, light triggered thyristor. Light triggered thyristor. So this light activation is very useful. We will see that for thyristors in the future. You will see if you want to deal with very high voltage, sometimes higher, let's say to 8,000 volts. Each thyristor can deal with 8,000 volts voltage, and you will see some thyristors are actually light triggered thyristors. All right. Static characteristics. This is, in general, similar to diode. Okay. Horizontal axis, voltage, vertical axis, current. And if you do not consider this part, let's see. If you do not consider this part, then this is similar to diode. Let's see if this curve is like this. This is diode, right? But thyristor is not diode. You have control. Based on how much current you inject to gate, the thyristor, if you do not control, let's say, for example, look at this curve first. If you do not inject gate current, that means Ig equal to 0, then there will be no current flowing through thyristor. So even if you increase the voltage across A and K, there will be very small current, just leakage. Until what? Until this voltage is too high. You are applying too high voltage, that voltage is exceeding the limit that this thyristor can sustain, then you turn it on. As I mentioned, if the voltage is too high, then it's turned on. When it's turned on, then the curve comes back to here. The voltage across, when it is turned on, the voltage across A and K will be getting very small. That's just the saturation voltage of those two transistors. And the current can be very high. Okay? That's when Ig is equal to 0. Okay? But when you inject some Ig, then you don't have to come to that high voltage. Then you can turn it on. You turn on the thyristor. As long as the gate current is getting larger, then you usually do not get too large voltage applied across the terminal A and K. Okay, so that's this part. This part is the difference between thyristor and diode. Because thyristor is a controllable, half-controllable device. If you do not inject gate current, then that curve is moving along this horizontal axis. Even when you apply high voltage, there will be no current. Okay? Only when you inject gate current, it will be similar to diode. So this part is quite easy to understand. Let's read through these statements. The thyristor will be blocking when reverse voltage, when it is reverse biased. For this part, that's similar. This part is exactly the same as diode. It will be blocking, no matter if there is gate current applied. Second statement, it will be conducting only when forward biased, only when you are applying positive voltage to A and negative voltage to K. And remember, there are two conditions. First condition, forward biased. Second condition, you have triggering current applied to the gate. Under these two conditions, thyristor will be turned on. Okay. Third one, once it is turned on, it will be latched on the conducting state. Latched. It will be latched on the conduction state. That means even when you take out the gate current, even when you remove the gate current, it will still be conducting. That's called latched. Okay. How do we turn it off? As we already discussed, the only measure that we can turn it off is to decrease the current to be nearly 0 with the effect of external circuit. Through external circuit, you decrease that current to 0, then thyristor turn off. Okay, so very simple static characteristics. Switching characteristics is a little more complicated. This is a picture showing the switching waveform of a thyristor. The upper side is the current flowing through thyristor. The lower side waveform is the voltage across the thyristor. Let's see, if we inject a gate current here at this time, we inject gate current at this time. Let me That's the gate current, Ig. Okay? Then, when you inject gate current, and when you apply positive voltage across A and K, the thyristor will be turned on. But this turning on has a process. It's not turned on immediately. There is a process. The thyristor voltage needs some time to decrease from certain value to very low voltage. Before it's turned on, the outside voltage is all applied to A and K. When it is turned on, between A and K, this voltage will be decreased to 0 because both those two transistors are driven to saturation region. The voltage across those two transistors will be very small. So in this case, the voltage will be decreased to 0 when it is turned on. And the current flowing through thyristor will be increasing. So you need some time. Okay? I'm sorry, this should be the time instant when you inject current into the gate should be here. Should be starting from this time instant. So you inject gate current through here at this time instant, and then you take some time Td for the current to start to increase. Let's see. Td is this time is the time for the current of the thyristor to start to increase. This is called delay time. This is called delay time, Td. And then, after this delay time, for the current flowing through thyristor to increase from certain level to up to the certain level, this is called current rising time or current rise time. Second time, rise time. Delay time, rise time. And then this total summation of Td plus Tr is called turn on time. So when you want to turn it on, starting from the time instant when you apply gate current until the current flowing through the thyristor is reaching the steady state, this time is called turn on time. You need this time to actually have the thyristor be turned on. Turn on time. Those two add up together. Okay? So when you turn it off, you also need certain process. Okay? Remember, as we said, the only method we can turn the thyristor off is through the external circuit to decrease the current, decrease the thyristor current to 0. Okay? But this process is very complicated. You see, let's say, for example, when you were starting from this point, starting from this time instant, we apply the negative voltage between A and K. We apply negative voltage between A and K. Therefore, we have the external current flowing through the thyristor gradually decreasing. But the similar thing to diode is that when this current is decreased to 0, at this time instant, when this current flowing through the thyristor decreased to 0, it would not stay at 0. You see? It will be changing direction and increasing. the current flowing through the thyristor will decrease to 0 and will not stay at 0. It will be increasing in the reverse direction. That reason is similar to what happens in diode, because there is still a lot of carriers, electrons and holes inside the thyristor. Therefore, when you apply negative voltage, you will still have current flow because of these carriers. Okay? And therefore, there will be negative current in the reverse direction and increasing. And when this current is lasting for a certain time, the carriers inside the 4 layers of thyristors will be swept out. Okay? After a certain time, this negative current will take all these carriers out. And then the thyristor gradually have the ability to block voltage. No longer, the conductivity is no longer high. The conductivity is getting back to nearly 0. And therefore, when all the carriers are removed, this thyristor become very high resistance. Okay? Therefore, the current can no longer be flowing through, because the conductivity of the thyristor now becomes very small, because all the carriers has been taken out. And at this time, the current will come back to 0, because conductivity is no longer high. So this process is very similar to what happens in diode. You have a reverse recovery process. This process is called reverse recovery process. Okay? That's similar to what happened in diode. Okay? And only in this case, after this point, the thyristor is now blocking reverse voltage. So you can see the reverse voltage now is applied across A and K. Okay? But after that, after this reverse recovery, thyristor is still different from diode. For thyristor, we still need certain time. We still need certain time resting. Actually, the thyristor will be resting for a certain time before you can apply positive voltage again from outside. That means after this point, after this time instant, if you suddenly change the position of outside voltage to positive again, then thyristor will be turned on, even if you have no gate current, because the thyristor is not recovered yet. The inside carriers are not very well distributed to block positive voltage yet. You need some time for the thyristor to rest. This time is called TGR. This is called forward recovery time. So only when you apply positive voltage after that, thyristor will not be turned on. Thyristor will recover the ability to block positive voltage. So if you do that, before this time instant, thyristor will be turned on, probably will be turned on, even if you don't have any triggering current. Okay? So, in general, if you want this thyristor to be turned on, turned off correctly, during the turning off process, the total turning off time is actually depending on the reverse recovery time and forward recovery time. You need to give the margin of the turn-off time larger than the summation of these two parts. If you turn it on before that, then the circuit will probably not working correctly. So you have to leave that time. That's turning off transient. Okay? So in the power converter, you have to pay attention to that if you use a thyristor. Turn it on, turn it off. For turning on, you have to make sure the turning on process, you leave the enough time for the thyristor to be turned on. That time should be larger than the turn on time. If you want to turn it off through the outside circuit, then you have to leave some turn off time for the thyristor to become to recover the ability to block forward voltage. Okay. There are specifications for thyristor similar to a diode. I will not get into details. You have to read through the textbook very carefully. I do not discuss in detail does not mean this is not important. Okay? Actually, this is very important. You have to spend a certain time on these definitions of specifications. For example, there are peak repetitive forward blocking voltage. The first one, that represents the maximum time, the maximum voltage the thyristor can sustain if you apply this voltage repeatedly. Okay, forward voltage. Remember, in the static characteristics, there is a maximum positive voltage maximum limit, and there is a reverse voltage maximum limit. If the voltage is higher than that, then the thyristor will be broken. There will be breakdown. Okay. These two specifications are usually used. Whichever is lower actually. Whichever is lower, it is used as the rated voltage. Or nominal voltage. So when you talk about, for example, if you see I bought a thyristor from the market and it is 1,000 volts thyristor, that 1,000 volts means what? Means those two things. The peak repetitive, either forward blocking voltage or reverse voltage is 1,000. The maximum voltage is 1,000. Okay? So the rated voltage for thyristor is actually depending on those two things. Another example is about the rated current. Okay, this is also very important. Usually we use this one, average on-state current. Use that one as the rated current. So when you see, let's say you have a 100 amp thyristor, if we see that, that means the average on-state current of that thyristor is 100 amp. But average on-state current has a special definition. I want you to pay attention to that. What is average on-state current? Average on-state current is usually defined as when you apply such kind of half sine wave current, half sine wave current flowing through the thyristor. Okay. Under this situation, the maximum average current, that this thyristor can sustain is called average on-state current. There is a very special definition about this one. So pay attention to this. The maximum average value of the current that a thyristor can sustain when this current is a half sine wave waveform is called average on-state current. Okay? So that you can see this is this rated current definition is really not very similar to the definition before. Usually when we talk about the rated current for other electric equipment, we use effective value. Okay, another name is RMS value, root mean square value. Okay, usually when you define a rated current for electric equipment, you use effective value. But this one is not using effective value. This one is using average value, maximum average value, and with a very special waveform. So when you select a thyristor, there is a little calculation. I want you to read through the textbook about this part and pay attention to that. When you select the thyristor, usually based on the effective value, because the reason a thyristor will be destroyed is that the power loss, energy loss in that thyristor is too high. And energy loss is actually producing heat. And if you want to evaluate the heat or energy loss on the thyristor, then you usually use effective value. If not, the current flowing through thyristor has an effective value exceeding the limit, then the thyristor will be destroyed. Okay? Then that means what? That means based on this on-state current, average current, let's say if it is 100 amp, you have to calculate how much effective value a thyristor can sustain. Okay? For example, if the average on-state current of thyristor is 100 amp, then you can convert that. You should calculate this into how much effective value of current this thyristor can sustain. That means you calculate this average value is 100 amp. You calculate how much is the effective value. Now I can give you the answer, but you find out why. The effective value is usually 1.57 multiplied by ITAV, the average, the on-state average current. So if the rated current for thyristor is 100 amp, then the maximum effective value of current it can sustain is 157 amp. So that's the basic conversion. Okay, I ask you to figure out why after the class. Okay, there are other examples. For example, holding current. Other specifications. Holding current. There is another one is latching up current. Holding current means when you turn on thyristor, when this current flowing through thyristor has reached the value higher than this holding current. Only when the actual current flowing through the thyristor is higher than its holding current, you can remove the gate current. You remove that gate current, the thyristor will still be turn on. That's called holding current. Okay. If the thyristor current is smaller than, when thyristor current is still smaller than holding current, and you take out the gate current, then the thyristor will be turned off. It will not be turned on. So that's the holding current. Latch up current means, did I make it wrong? Okay, I believe I make it wrong. Latch up current is the current I just mentioned. Latch up current means only when the thyristor current is larger than the latch up current, you can remove the gate current. Okay? Holding current means what? Holding current means when the thyristor current is getting smaller than this value, smaller than the actual current IA is smaller than IH, then we can consider this thyristor turned off. Okay? It doesn't have to be exactly equal to 0. If you want to turn off thyristor, the current doesn't have to be exactly equal to 0. The condition is that as long as the current is smaller than IH, then this thyristor is turned off. Okay? So we'll get into the details of all these specifications. I will not get into details in the class. Okay? There are a family of different thyristors, different types of thyristors. Other than the general, ordinary thyristor, there is fast switching thyristor. Fast switching thyristor. That means the turning on and the turning off process of this thyristor is very fast. Faster than ordinary thyristor. And then you can imagine these thyristors are used for the situation when you need to turn on and turn off thyristors very fast. Okay. Second, trialed AC switch. Trialed AC switch, there is a short name for that, triac. Triac, another name is bidirectional triode thyristor. Triac. Okay. It is actually what? It is actually the connection of two thyristors. If you look at this picture here, it is actually the connection of two thyristors. This connection is what we call back-to-back connection. Back-to-back connection. Okay. Another name for back-to-back connection is antiparallel. Antiparallel connection. Okay. So you are connecting two thyristors in antiparallel mode. Because we know a thyristor can only allow one direction current flow. One thyristor can only allow one direction current flow from A to K. So if you want to control the other direction current flow, then you need another thyristor, an antiparallel thyristor. Okay? And the IV curve, IV characteristics of a triac is like this. In both directions, in positive direction, you can control the turn on of the thyristor. In the negative direction, when you apply negative voltage, then it is the other thyristor to control the turning on of that thyristor, to control the conducting or blocking of that current. So for both directions, you have the ability to control the current flow. That's triac. Third one is reverse conducting thyristor. This is also very simple. It is actually the antiparallel connection of one thyristor with one diode. That means in this direction, I have the ability to control the conducting and the blocking of current flow through gate. But on the other side, on the other direction, from K to A, it is a diode. Okay? I cannot control that through gate, but it is a diode. This is called reverse conducting thyristor. Okay? And then the last one, both of these, they have special symbol. Triac has a special symbol like that. Reverse conducting thyristor has a symbol like this. You see, pay attention to this line here. That represents reverse conducting. Okay? And then the last one I want to mention is light-triggered thyristor. I have already mentioned this. You are shedding some lights on the gate area to turn a thyristor on. LTT, light trigger thyristor. Okay. Okay, that's exactly all the material for thyristors. Homework. The Chinese textbook. On page 42, problem 1, 2, 3, 4, 5. 1 to 5. I want you to translate that into English and complete your answer also in English. Okay? And send in to our TA through email. Send in your homework through email. All right? Any questions? Translate the problem into English. And okay? Any other questions? Yes. Due time? You discuss with your TA. Set up a due time. All right. I'll see you next week.